What if everything we see when we look up at the night sky is just the tiniest fraction of reality? The universe stretches farther than our most powerful telescopes can reach, hiding secrets so profound they challenge our very understanding of existence. Out there, at the edge of everything we know, lies a frontier where the rules of physics twist, where light bends in ways that defy logic, and where entire galaxies might vanish into the void without a trace. This is where the cosmos keeps its most baffling mysteries waiting for us to uncover them. Picture this, a boundary so distant that even light from the dawn of time hasn't reached us yet. A place where space itself might ripple like fabric, where dark energy pushes galaxies apart faster than the speed of light, and where some scientists believe parallel universes could brush against our own. How far does space really go? Does it even have an edge? For centuries, these questions have haunted astronomers, philosophers, and dreamers alike. And today, we stand closer than ever to unraveling them, but the answers might be stranger than anything we've dared to imagine. That's exactly what we're diving into today. 30 of the most astonishing mysteries lurking at the edge of the universe. From colossal cosmic voids where nothing should exist to eerie signals that hint at dimensions beyond our own, to the chilling possibility that our entire cosmos is just one bubble in an infinite foam of universes. Each one of these enigmas pulls us deeper into the unknown, forcing us to rethink what we thought we knew about reality. So if you're ready to journey to the farthest reaches of space, where the laws of physics unravel and the impossible becomes possible, then buckle up. Because by the end of this, the night sky will never look the same to you again. The first great mystery lies right at the limit of what we can see, the boundary of our observable universe. Think of it like standing on the shore of an endless ocean, where no matter how hard you squint, the horizon always stays just out of reach. That's where our cosmic vision ends. Not because there's nothing beyond it, but because the light from those distant regions hasn't had enough time to reach us since the Big Bang. Space is still expanding, stretching the fabric of reality itself, which means some galaxies are moving away from us faster than their light can travel back to our telescopes. They've crossed a point of no return, vanishing behind what scientists call the cosmic horizon. But here's where things get truly mind-bending. Just because we can't see past this edge doesn't mean nothing's there. In fact, most cosmologists believe the universe stretches far beyond what's visible to us, possibly forever. Some theories even suggest our entire observable cosmos might be just one tiny bubble in an infinite sea of other universes, each with its own unique physics, stars, and maybe even alien forms of life. Imagine that island universes adrift in some greater cosmic ocean, completely cut off from one another by unimaginable distances. This raises an unsettling question. If we're trapped inside our own observable bubble, how could we ever prove what lies beyond? Some researchers hunt for subtle distortions in the cosmic microwave background, the afterglow of the Big Bang that might hint at collisions with other universes in the distant past. Others study the strange, large-scale patterns of galaxies for clues that our universe might be rubbing up against something else. One thing's certain, the edge isn't just a barrier, it's a doorway to questions that could rewrite everything we know about existence itself. Now imagine a force so powerful it's dragging entire galaxies, including our own, toward some unseen cosmic giant. Hidden behind the thick veil of stars and dust in the Milky Way's disk lies one of the universe's strangest enigmas, the Great Attractor. This immense gravitational anomaly has been pulling thousands of galaxies toward it at speeds topping 2 million kilometers per hour, and for decades, its true nature remained obscured by what astronomers call the zone of avoidance, a region so crowded with cosmic debris that our telescopes could barely peer through. Think of it like trying to spot a lighthouse through a hurricane. The Milky Way's own structure was blocking our view of something monumental, but what could exert such an irresistible pull? Early theories suggested a supercluster of galaxies, a dense knot of matter with gravity strong enough to bend the paths of entire galactic neighborhoods. Yet when researchers finally managed to glimpse past the zone of avoidance using X-ray and infrared telescopes, they found something even more puzzling. The Great Attractor wasn't nearly massive enough to explain the motion of all those galaxies. Something else, something invisible, had to be lending a hand. That's where dark matter enters the story. This mysterious substance, which makes up roughly 85% of the universe's mass, could be woven into colossal filaments stretching across the cosmos, funneling galaxies toward the Great Attractor like rivers flowing into a waterfall. But here's the twist: the Great Attractor itself might just be a waypoint on an even larger cosmic journey. Recent observations suggest an enormous structure called the Laniakea supercluster, a web of galaxies spanning 500 million light-years, is pulling everything, including the Great Attractor, toward an even more distant and massive region known as the Shapley supercluster. It's as if we've been following breadcrumbs through the universe, only to realize the trail leads to a feast we can't fully see yet. This raises a profound question: how many more of these cosmic giants are out there hiding in plain sight? If something as colossal as the Great Attractor could stay concealed for so long, what else might be lurking beyond our current maps? Every time we think we've charted the universe, it humbles us with another layer of mystery, reminding us that even the mightiest gravitational forces might just be whispers in a much grander conversation. Somewhere in the vast cosmic web, where galaxies typically cluster together like cities dotting a nighttime landscape, there exists a place so empty it defies logic. The Boötes void, a spherical chasm stretching an astonishing 1 billion light-years across, contains hardly any galaxies at all. To put that into perspective, if our Milky Way were floating in this void, astronomers in neighboring galaxies wouldn't have discovered us until the late 20th century because the space between us would be nearly unfathomably barren. Most voids are like rural areas between galactic metropolises, but the Boötes void is more like a desert the size of a continent, silent, dark, and almost completely untouched by starlight. What makes this emptiness even stranger is that it shouldn't exist according to our best models of the universe. The Big Bang's afterglow shows a remarkably even distribution of matter in the early cosmos, so how did this cosmic vacancy form? Some scientists argue it's merely a statistical anomaly, a random fluctuation in the grand lottery of galaxy formation, but others whisper about far wilder possibilities. Could quantum fluctuations in the infant universe have stretched into titanic bubbles of nothingness? Or might this void be the imprint of something ancient and unimaginable, like a collision between our universe and another in the multiverse? The theories get even more unsettling when you consider what is lurking in the void. The handful of galaxies found there aren't scattered randomly. They're clustered along faint, thread-like structures as if clinging to invisible lifelines. Some researchers suggest these filaments could be scars from a cosmic battle, where an earlier generation of galaxies was somehow erased. Others propose the void might be filled with dark matter so dense it stifled star formation entirely, leaving behind a ghostly skeleton of what should have been. But here's the most haunting question of all. Is the Boötes void unique, or are there others like it hiding in plain sight? Modern sky surveys reveal other curious gaps, some nearly as vast, lurking in the cosmic shadows. Each one forces us to confront how little we truly understand about the architecture of the universe. We map the heavens assuming matter spreads evenly, yet these voids laugh at our assumptions, reminding us that the cosmos might be far stranger, far emptier, and far more mysterious than we ever dreamed. We take for granted that space stretches on forever in every direction, but what if the universe itself has a shape, one that bends and curves in ways we can barely comprehend? The question of whether the cosmos is flat like a sheet of paper, round like a balloon, or warped like a saddle isn't just academic. It could determine the ultimate fate of everything, whether the universe will expand forever, collapse back on itself, or tear apart at the seams. Clues to this cosmic geometry are hiding in the oldest light we can see, the cosmic microwave background, or CMB. This faint glow is the remnant heat from the Big Bang, a snapshot of the infant universe frozen in time. When scientists analyze its patterns, they're essentially measuring the shadows cast by the shape of space itself. If the universe were positively curved like a sphere, light from the CMB would converge, making distant hotspots appear larger than they really are. If it were negatively curved like a saddle, those spots would stretch and distort. But after decades of painstaking measurements from satellites like Planck to ground-based telescopes, the data points overwhelmingly to a flat universe, one where parallel lines never meet and the angles of a triangle always add up to 180 degrees. Yet here's the catch: flat doesn't necessarily mean infinite. Imagine an ant crawling on a Mobius strip. It could walk forever in what seems like a straight line, only to end up right where it started. Some theorists argue our universe might work the same way, looping back on itself in hyperspace so subtly that we'd never notice. If that's true, a spaceship traveling far enough in one direction might, after billions of light years, return to its starting point without ever turning around. But the debate gets even stranger when you consider anomalies in the CMB. Certain large-scale patterns appear weaker than they should be, as if part of the universe's energy has leaked out. Could this hint at a more complex topology, like a cosmic hall of mirrors where space folds in on itself? Or does it suggest we're seeing only a fraction of reality, with the true shape of the universe lurking beyond our observational horizon? The terrifying beauty of this mystery is that we may never know for sure. A flat universe could still be immeasurably vast, with regions so distant their light will never reach us. Or it might be finite but unbounded, twisting in higher dimensions we can't perceive. One thing's certain: the cosmos refuses to fit neatly into our human-scale intuitions. Every answer unravels new questions, leaving us staring at the stars, wondering if we're standing on a speck of dust, or a ribbon that stretches beyond all comprehension. Somewhere beyond the edge of the observable universe, something is pulling. Not just a gentle tug, but a relentless current dragging thousands of galaxy clusters in the same direction at speeds that defy explanation. Astronomers call this phenomenon dark flow, a mysterious cosmic drift where entire superclusters are caught in what looks like a river of space itself, all streaming toward a single patch of sky near the constellations Centaurus and Vela. It's as if the universe is tipping its hand, revealing a hidden force so vast it can move the largest structures we know like leaves on a wind. At first, scientists thought it might be a measurement error, some glitch in the data from the cosmic microwave background. But when satellite after satellite confirmed the same eerie motion, the implications became impossible to ignore. These galaxy clusters are moving too fast and too uniformly to be explained by the gravitational pull of anything within our observable universe. Even the colossal Shapley supercluster, the largest concentration of mass we've mapped, can't account for the scale of this motion. That leaves two spine-tingling possibilities. Either our understanding of gravity is fundamentally flawed, or something outside our universe is exerting an invisible influence. Imagine standing in a boat drifting downstream, only to realize there's no river, just an ocean stretching endlessly in every direction. That's the unsettling premise behind one leading theory. That dark flow is evidence of other universes brushing against ours in the multiverse. According to this idea, space beyond our cosmic horizon might be packed with bubble universes, each with its own physical laws. If one of these bubbles passed close enough, its gravity could ripple into our own universe, tugging galaxies toward it like a magnet. But not everyone's convinced. Skeptics argue that peculiar velocities, random motions left over from the early universe, might add up to look like a coordinated flow when seen at large scales. Others propose exotic forms of dark matter or energy could be warping space-time in ways we don't yet understand. The most controversial suggestion, that dark flow is a remnant of the Big Bang itself, a cosmic fingerprint showing our universe was born lopsided, with an inherent directionality written into its very fabric. What makes this mystery so gripping is that it forces us to confront the limits of our cosmic vision. If the flow is real, it implies structures so enormous they dwarf our observable universe, structures we may never directly see. Yet every galaxy cluster caught in this current is like a message in a bottle, hinting at a reality far grander than we've dared to suppose. Whether it's other universes, unknown physics, or something even stranger, one thing's clear: the cosmos is moving, and we're only just beginning to understand why. Two of the most trusted tools in cosmology, the cosmic microwave background and exploding stars, are telling us wildly different stories about how fast the universe is growing. This isn't just a small rounding error, it's a full-blown crisis called the Hubble tension, and it threatens to upend our understanding of cosmic history. On one side, we have measurements from the Planck satellite, which studies the faint glow of the Big Bang's afterglow. According to this data, the universe should be expanding at about 67 kilometers per second for every megaparsec of space, a speed that fits neatly with our models of dark matter and dark energy. But when astronomers turn to distant supernova stellar explosions so predictable they're called standard candles, they get a different number entirely. These dying stars suggest the universe is sprinting along at 73 kilometers per second per megaparsec. That gap might seem tiny, but after 14 billion years of compounding, it means the cosmos is expanding nearly 10% faster than our best theories predict. So who's wrong? The eerie truth is that both methods are incredibly precise and both refuse to budge. The cosmic microwave background captures the infant universe frozen in time, while supernova act as mile markers in space, letting us measure expansion directly. Neither approach shows signs of a technical flaw, which leaves only one unsettling possibility. There's a gap in our physics. Some hidden force or undiscovered particle might be nudging the universe apart faster than expected. Maybe dark energy isn't constant but grows stronger over time. Or perhaps gravity itself behaves differently on cosmic scales, warping space in ways Einstein never anticipated. The most electrifying theory: that we're seeing fingerprints of an extra dimension, a hidden layer of reality subtly altering how the universe stretches. Others suggest early quantum fluctuations might have carved cosmic bubbles, leaving our corner of space unusually sparse and prone to faster expansion. But the wildest idea of all is that the Hubble tension isn't a mistake at all, but a clue that we need to scrap our models entirely and start fresh. What makes this mystery so urgent is that it's not just academic, it cuts to the heart of whether we truly understand the universe's birth, life, and ultimate fate. A faster expansion rate could mean galaxies will vanish over the horizon sooner, leaving future civilizations with a sky nearly empty of stars. Or it might hint at cosmic cycles we've yet to imagine, where universes breathe in and out like living things. Until we solve it, one thing's certain: the cosmos is hiding something fundamental, and every telescope on Earth is racing to uncover what it is. If the universe has an edge, what would it even look like? We're so accustomed to thinking in terms of boundaries, walls, borders, horizons, that the idea of a cosmos without limits feels almost impossible to grasp. Yet everything we observe suggests space stretches far beyond what we can see, leaving us with a haunting question: is there a true end to it all, or does the fabric of reality simply go on forever? The answer might be stranger than anything we've imagined. One radical possibility is that our universe isn't floating alone in nothingness, but is instead one of countless bubble universes in an eternally inflating multiverse. Picture a pot of boiling water, with each bubble representing a separate cosmos, each with its own unique physics. In this scenario, the edge of our universe wouldn't be a cliff into emptiness, but a delicate membrane where our bubble presses against others, perhaps even brushing against realities where gravity is stronger, light moves slower, or time flows backward. The scary part, if these bubbles collided, the collision could ripple through space as a catastrophic shockwave, rewriting the laws of physics in its wake. Then there's the brain-world hypothesis, a theory straight out of string theory's wildest dreams. Imagine our entire universe as a three-dimensional sheet, a brain, floating in a higher dimensional space. In this model, the edge might not be a place at all, but a dimensional fold like the hem of a curtain tucked into unseen layers of reality. Gravity could be leaking into our universe from these hidden dimensions, explaining why it feels so weak compared to other forces. If true, the real boundary of existence might be inches away in a direction we can't perceive, like ants unaware of the world above their flat ground. But the most unsettling idea, that the universe does have a hard edge, a fiery wall of energy, or a cosmic no-go zone where space-time itself frays into chaos. Some models suggest such a boundary could form if our cosmos is a simulation, with the edge acting like the processing limit of some unfathomable computer. Others propose it might be a relic of the Big Bang, a scar where inflation slammed on the brakes, leaving behind a seething barrier of primordial particles. If we somehow reached it, would we find an impenetrable veil, or would crossing it catapult us into another layer of existence entirely? The irony is crushing. Even if an edge exists, we may never reach it. The universe's expansion is accelerating, pushing potential boundaries farther away faster than light can travel. By the time we built a ship capable of the journey, the edge might have receded beyond all hope of detection. That's the true puzzle, not just what lies at the end of space, but whether the cosmos will forever keep its greatest secret just out of reach. Buried in the cosmic microwave background, the afterglow of the Big Bang, there's a patch of sky so cold it sends chills down the spines of cosmologists. Dubbed the cold spot, this enigmatic region glows dimmer than its surroundings by a fraction of a degree, a tiny deviation that shouldn't exist according to our standard models of the universe. At first glance, it might seem trivial, a cosmic hiccup in the data. But when you consider this spot spans nearly 2 billion light-years across, the mystery deepens. Something colossal must have left its mark here, and the leading theories sound like they're ripped from science fiction. One explanation points to a supervoid, an unfathomably vast emptiness where galaxies are eerily scarce. In such a region, light from the CMB would lose energy as it traverses the void, a phenomenon called the integrated Sachs-Wolfe effect. Think of it like rolling a marble uphill. The effort saps its momentum, leaving it slower on the other side. If the cold spot is indeed a void, it would need to be the largest ever discovered, dwarfing even the Boötes void. But here's the catch. Recent galaxy surveys haven't found enough missing matter to account for the temperature drop. The numbers don't add up, leaving astronomers scratching their heads. Then there's the far more tantalizing possibility. The cold spot might be a bruise from a collision with another universe. In the chaotic frenzy of the multiverse, where bubble universes jostle like soap suds, a neighboring cosmos could have bumped into ours long ago. The energy released in such a crash would have left a distinct imprint, a cold, circular blemish in the CMB. Supporters of this idea point to the spot's unusual sharp edges and its alignment with other anomalies in the cosmic microwave background. It's as if the universe is holding up a sign saying, "Look here, something extraordinary happened." But not everyone's ready to leap to multiverse conclusions. Skeptics argue it could just be a statistical fluke, a random fluctuation in the noise of the early universe. After all, when you're mapping something as vast as the CMB, quirks are bound to appear. Others propose more exotic physics, like primordial black holes distorting space-time or dark energy behaving differently in this region. The cold spot might even hint at a flaw in our understanding of inflation, the rapid expansion of the universe moments after the Big Bang. If expansion wasn't perfectly uniform, it could have left behind pockets of uneven temperature, like dough that didn't bake evenly. What makes this mystery so gripping is its sheer audacity. If the cold spot is evidence of another universe, it would be the first tangible clue that we're not alone in the multiverse. But if it's just a void or a glitch, it's a humbling reminder of how much we still don't know about the cosmos. Either way, this frigid anomaly is more than a curiosity. It's a cosmic detective story, one that challenges us to question everything we thought we understood about the fabric of reality. And until we solve it, the cold spot will remain one of the universe's most tantalizing frozen secrets. Time doesn't just pass, it unravels. And at the edge of the universe, where the last stars flicker out and galaxies fade into darkness, we're forced to confront a chilling possibility. What if time itself has an expiration date? Not just a pause, but a full stop where the concept of before and after ceases to exist. This isn't science fiction. It's a real cosmic countdown dictated by the slow, inevitable march of entropy, the universe's relentless slide toward disorder. Picture a clock winding down. Every action, from the fusion inside stars to the firing of neurons in your brain, steals a bit of usable energy from the cosmos, scattering it as waste heat. Eventually, when the last black hole evaporates and space reaches perfect thermal equilibrium, a state scientists call heat death, there'll be no energy left to power change. No stars burning, no particles moving, just an endless, uniform sea of lukewarm nothingness stretching forever. In this frozen wasteland, time loses all meaning. Without events to mark its passage, does it even exist? But heat death might not be the only way time could end. Some theories suggest a far more violent finale. Imagine a mysterious force called phantom energy, a twisted cousin of dark energy that grows stronger as the universe expands. If this exists, it could accelerate expansion to the point where space-time itself tears apart, not just stretching, but shredding atom from atom in a catastrophic big rip. In this scenario, time wouldn't fade away, it would be annihilated in an instant, like a movie screen ripped mid-scene. The terrifying beauty of these theories is that they force us to redefine time not as a fundamental backdrop, but as an emergent property, a side effect of the universe's busy, fluctuating energy. Like a flame that only exists while fuel burns, time might be inextricably linked to activity. No motion, no time, and that raises an even deeper question. If time can stop, could it also restart? Some models of cyclic universes suggest that after heat death, quantum fluctuations might birth a new Big Bang, resetting the cosmic clock. But here's the twist: we might never know. If time ends at the universe's edge, any evidence would be locked beyond a horizon we can't cross. The final tick of the cosmic clock could be ringing right now in some distant void, and we'd have no way to hear it. That's the ultimate paradox. The end of time might be the one event the universe refuses to let us witness. There's a pattern hidden in the cosmic microwave background so bizarre that scientists nicknamed it the axis of evil, not because it's malevolent, but because it threatens to upend everything we thought we knew about the universe's origins. This spine-chilling alignment refers to a series of peculiar anomalies in the CMB, the oldest light in existence, that seem to correlate eerily with the plane of our solar system. It's as if the universe's blueprint has a strange, inexplicable connection to our tiny corner of space, a connection that, by all rights, shouldn't exist. When the Planck satellite mapped the CMB in exquisite detail, researchers expected to see randomness, a uniform scatter of hot and cold spots left over from the Big Bang's turbulent infancy. Instead, they found something that defied logic. Certain large-scale fluctuations appeared to align along an axis that suspiciously mirrors the ecliptic, the path the sun and planets trace across our sky. The odds of this happening by chance, less than 1 in 1,000. It's like rolling dice 1,000 times and getting snake eyes every single time. Statistically, it shouldn't happen unless something's rigging the game. So what's behind this cosmic conspiracy? Skeptics argue it's just a fluke, an artifact of measurement errors or subtle biases in how we process CMB data. After all, our solar system isn't special. Why would the universe's structure care about our little planetary neighborhood? But the more we refine our instruments, the harder it becomes to dismiss. Some theorists suggest it might reveal a flaw in our understanding of inflation, the rapid expansion of the early universe. If space didn't stretch perfectly evenly, it could have left behind wrinkles that just happened to line up with our solar system purely by accident. Then there are the more radical explanations. One unsettling possibility is that we're seeing evidence of a preferred direction in the cosmos, a fundamental asymmetry baked into space-time itself. Imagine the universe isn't uniform in all directions but has a grain like wood, with structures forming more easily along certain axes. This would violate the cosmological principle, the bedrock assumption that the universe looks roughly the same no matter where you're standing. If true, it would force us to rewrite physics textbooks, but the wildest theory that the axis of evil is a glitch in the matrix, a shadow of some cosmic simulation we're unknowingly trapped inside. In a virtual universe, computational shortcuts might leave behind telltale patterns, much like pixelation in a video game. If the simulation's code aligns certain features with its reference frame, it could explain why the CMB's anomalies sync up with our solar system. It's a controversial idea, but even prominent physicists admit it's hard to entirely rule out. The chilling beauty of this mystery is that it forces us to confront how much we still don't understand about reality's fabric. Whether it's a measurement quirk, a cosmic accident, or something far stranger, the axis of evil remains one of the universe's most tantalizing puzzles. A whisper that maybe, just maybe, we're missing something fundamental about how it all fits together. One of the most unsettling realizations in modern astronomy is that some stars seem to defy cosmic history, appearing billions of years older than the universe itself. Take Methuselah, a faint star hovering near the edge of our galaxy. By measuring its chemical composition and brightness, astronomers pinned its age at a jaw-dropping 14.5 billion years. There's just one problem. The universe, according to our best estimates, is only 13.8 billion years old. That's like finding a birth certificate claiming you're older than your own parents. How can stars exist before the cosmos itself? The answer lies in the delicate art of cosmic timekeeping. Calculating a star's age relies on tracking its nuclear fuel, the heavier elements fused in its core, and modeling how quickly it burns through them. For Methuselah, initial measurements suggested an impossibly ancient origin. But here's where things get slippery. These calculations depend on assumptions about the star's distance and composition, which aren't always precise. Recent Hubble data adjusted Methuselah's position, nudging its estimated age down to about 12 billion years. That still edges uncomfortably close to the universe's birthday, but the gap isn't as glaring. Yet the mystery doesn't end there. Across the cosmos, other anomalies lurk. Globular clusters, dense swarms of stars orbiting galaxies, often appear older than their surroundings. Some even contain stars with barely any heavy elements, suggesting they formed before supernova could seed the universe with metals. Then there's redshift, the stretching of light from distant galaxies that reveals how fast they're moving away from us. Certain measurements suggest pockets of the universe might be expanding at different rates, skewing our perception of time and distance. If space-time isn't uniform, could our cosmic clock be ticking differently in different places? This raises an even deeper question. Is the Big Bang's timeline itself flawed? The universe's age is calculated by tracing backward from its current expansion rate, but what if that rate wasn't constant? Some theorists propose a bouncing cosmology, where our universe emerged from the collapse of a previous one, making the true age unknowable. Others suggest dark energy's influence might have warped early expansion, throwing off our estimates. There's even a fringe idea that time flowed differently in the universe's infancy, a concept called varying speed of light, where fundamental constants weren't so constant after all. What makes this puzzle so fascinating is that it forces us to question not just the stars, but the very tools we use to study them. Every dating method, from radioactive decay to stellar physics, rests on assumptions about how nature behaves, assumptions that might not hold true in the extreme environments of the early cosmos. Until we find a star that openly defies the laws of physics or redefine our understanding of time itself, the universe's true age will remain one of its most tantalizing enigmas, a reminder that even our most precise calculations are just whispers in the dark, trying to decode a story written billions of years before we existed. Imagine a galaxy so ghostly it shouldn't exist. NGC 1052 DF2 drifts through space like a cosmic mirage, a sprawling collection of stars with barely any gravity to hold them together. Normally, galaxies are wrapped in thick halos of dark matter, the invisible glue that keeps them from flying apart. But this phantom galaxy seems to float freely, almost completely devoid of the mysterious substance that supposedly makes up 85% of the universe's mass. The discovery sent shockwaves through astronomy because if dark matter is truly universal, how could an entire galaxy escape its grasp? At first glance, the numbers seem impossible. Measurements showed DF2 stars moving far slower than they should be without dark matter's gravitational pull. Some clusters within it barely cling together like a sandcastle at high tide. When researchers calculated the galaxy's total mass based on visible stars alone, everything added up perfectly. There was no missing mass to account for. This flies in the face of everything we've observed in other galaxies, where stars orbit so fast they'd escape without dark matter's extra tug. It's as if someone removed the invisible scaffolding holding up a skyscraper, yet the building somehow still stands. The immediate assumption was that DF2 must be a fluke, an outlier forged by some bizarre cosmic accident. One theory suggests it might be the shattered remains of a larger galaxy, stripped of dark matter during a violent collision billions of years ago. Picture two galaxies colliding like clouds of smoke, where ordinary matter slows down and clumps together while dark matter, barely interacting, sails right through. Over eons, the visible stars could reassemble into a new structure, leaving their dark counterpart long gone. But then astronomers found more of these renegade galaxies. NGC 1052 DF4, UDG 44, and others joined the ranks of dark matter-free anomalies. Each one raises the same unnerving question: what if we've been wrong about gravity all along? A small but vocal group of physicists argues these galaxies point to flaws in our theories, favoring an alternative called modified Newtonian dynamics, or MND. This idea suggests gravity behaves differently at cosmic scales, eliminating the need for dark matter entirely. Instead of invoking invisible particles, MND tweaks the equations themselves, predicting how gravity weakens more slowly over vast distances. Yet the majority of scientists remain unconvinced. Critics point out that MND struggles to explain other cosmic phenomena, like the Bullet Cluster, where colliding galaxies clearly separated their visible matter from their gravitational pull, leaving dark matter's fingerprints unmistakable. Others propose DF2 might still harbor dark matter, just in an unusual configuration. Perhaps its dark halo was stretched thin by tidal forces, or maybe measurement errors underestimated its true mass. The debate grows even more heated with recent observations of another ghostly galaxy, DF44, which initially appeared dark matter-free but upon closer inspection might contain traces after all. What makes this mystery so electrifying is that it cuts to the heart of how we understand the cosmos. If dark matter-free galaxies are real, they could rewrite the rules of astrophysics. If they're illusions, they force us to confront the limits of our instruments and assumptions. Either way, these cosmic phantoms remind us that the universe still holds puzzles capable of shaking even our most cherished theories, proving that when it comes to the edge of understanding, we're all just stargazers chasing shadows. The cosmic microwave background, the universe's oldest light, reveals something bizarre. No matter where you look, the temperature is almost exactly the same, down to a few millionths of a degree. It's as if someone took a colossal paintbrush and smoothed the entire cosmos to perfect uniformity. But here's the catch: regions of space on opposite sides of the observable universe are so far apart that light, or anything else, couldn't possibly have traveled between them in the time since the Big Bang. So how did they sync up their temperatures so perfectly? This is the horizon problem, and it's one of cosmology's greatest unsolved puzzles. Picture two strangers on opposite ends of a stadium wearing identical outfits without ever seeing each other. That's essentially what the early universe did, except these strangers were separated by billions of light years, with no possible way to exchange information. According to the standard Big Bang model, heat should have varied wildly across space, with some regions blazing hot while others froze cold. Instead, we find an eerie symmetry, as if the cosmos came pre-calibrated. The leading explanation is cosmic inflation, a theory proposing that the universe underwent a mind-bending expansion in the first tiny fraction of a second after the Big Bang. Imagine a speck of space stretching to the size of a grapefruit faster than light itself could blink, smoothing out wrinkles like inflating a balloon. In this scenario, regions that seem impossibly distant today were once neighbors, close enough to exchange heat before inflation hurled them apart. It's a neat solution, but not without holes. Inflation predicts gravitational waves that we've yet to detect conclusively, and some theorists argue it's too flexible, able to explain almost any observation retroactively without offering definitive proof. That's led to wilder ideas. Could quantum entanglement, where particles instantly influence each other regardless of distance, have linked far-flung parts of the early universe? Or did spacetime emerge from a deeper, pre-existing structure where uniformity was baked in from the start? Some daring models even suggest our universe might be a hologram, with all its events encoded on a distant boundary, making uniformity an illusion of projection. The most unsettling possibility, that we're seeing evidence of a cyclical universe, one that's lived and died countless times, each iteration leaving behind subtle traces in the next. If true, the uniformity might not be a mystery at all, but the cosmic equivalent of genetic memory passed down through cycles of birth and collapse. Until we find definitive answers, the horizon problem remains a haunting reminder. The universe might be hiding its greatest secrets in plain sight. Stretching across 3.3 billion light-years, a full 15th of the observable universe, the giant arc dangles through space like a cosmic necklace strung with galaxies. This monstrous structure, discovered in 2021, defies one of cosmology's most fundamental principles, the idea that matter should be distributed evenly at the largest scales. Instead, it hangs there, a near-perfect curve of galaxies, galaxy clusters, and vast clouds of gas, so immense it would take light 3 billion years to travel from one end to the other. The sheer size isn't just impressive, it's theoretically impossible. According to our best models, structures this colossal shouldn't have had enough time to form after the Big Bang, leaving astronomers scrambling for explanations. What makes the giant arc even stranger is its shape. Unlike typical galaxy clusters or superclusters which clump together like ink blots, this structure traces a deliberate, almost geometric arc across the sky. Imagine drawing a line connecting the dots of distant city lights, except these dots are entire galaxies, each containing billions of stars. Some researchers compare it to a fossilized ripple in spacetime, a relic of primordial sound waves that once echoed through the infant universe. In those first moments after the Big Bang, matter wasn't silent, it pulsed with oscillations much like a ringing bell. These pressure waves, known as baryon acoustic oscillations, left faint imprints in the cosmic microwave background. But the giant arc scale dwarfs even those expected patterns, as if someone cranked the universe's volume to 11. One radical theory suggests it might be evidence of cosmic strings, hypothetical defects in space-time left over from the universe's fiery birth. Picture the early cosmos cooling like molten glass, forming cracks as it solidified. These ultra-dense, thread-like flaws could have warped gravity around them, funneling galaxies into eerie alignments. If true, the giant arc wouldn't just be a curiosity, it would be a direct window into physics far beyond our current understanding, a scar from when reality itself was still setting into place. Yet not everyone's convinced the arc is real. Skeptics argue it could be a trick of perspective galaxies that only appear aligned from our viewpoint, like distant streetlights lining up by chance. To test this, astronomers are mapping the structure in 3 dimensions, weighing each galaxy's distance against its position. Early results suggest the arc holds up, but the debate rages on. Even if it's confirmed, the deeper question remains: are we seeing a fluke, or does the giant arc hint that the universe's largest structures play by rules we've yet to discover? Perhaps the most unsettling possibility is that this colossal curve is just the beginning. If one structure this size exists, others might lurk in the cosmic shadows, waiting to upend our models entirely. Every time we think we've grasped the universe's architecture, it throws another curve, literally reminding us that the cosmos operates on scales and timelines too vast for human intuition. The giant arc isn't just a mystery, it's a humbling lesson that even the grandest patterns we uncover might still be fragments of something far larger, far stranger, and far beyond our current comprehension. Black holes aren't just cosmic vacuum cleaners, they're information shredders. When matter vanishes beyond their event horizons, it leaves behind a haunting question: what happens to all the data that once described it? This is the black hole information paradox, a puzzle so profound that even Einstein's theories tremble at its implications. Normally, quantum mechanics insists that information can never truly vanish. It might get scrambled beyond recognition, but it's always preserved, like rearranging the letters of a book into gibberish rather than burning it. Yet when Hawking radiation causes black holes to slowly evaporate, it seemingly leaves no trace of the particles they swallowed. If this paradox holds for singularities, what does it mean for the universe itself, especially at its farthest edges, where entire galaxies might be slipping past the ultimate cosmic horizon? Picture the universe's edge as a titanic black hole boundary, not just pulling in stars and gas but erasing their histories from existence. Every photon, every atom that crosses this threshold would carry with it the story of its origin, the heat of ancient supernova, the fingerprints of long-dead civilizations. If information can't be destroyed as quantum laws demand, then these stories can't just wink out of existence. So where do they go? One radical proposal suggests they're encoded on the universe's horizon itself, like a cosmic hard drive. Just as holograms store 3D images on 2D surfaces, the fabric of spacetime might preserve swallowed data in imprints we can't yet decode, but there's a catch. If information lingers at the boundary, it would violate relativity's core tenet, that no observer, whether inside or outside the horizon, witnesses anything unusual at the point of crossing. A falling astronaut wouldn't feel a firewall of data at the edge, yet an outside watcher would insist it's there. This contradiction splits physics into warring camps. Some argue the information is smeared across time, leaking back via Hawking radiation in quantum whispers. Others propose it's funneled into baby universes, hidden pockets of reality branching off from our own. The wildest idea, that the paradox is a clue we're missing a deeper layer of physics, one where space, time, and information intertwine in ways we've yet to imagine. Now stretch this problem to the universe's edge. If our entire cosmos has a boundary, does it too obey these rules? When galaxies redshift out of view, their light stretched to nothingness by accelerating expansion, is their data truly lost or just trapped on a horizon we'll never reach? The terrifying beauty of this mystery is that it forces us to confront the nature of reality itself. maybe the universe's edge isn't a wall but a mirror, reflecting every bit of information back in forms we don't yet understand. Or perhaps, like a cosmic magician's trick, the data isn't gone at all, just hidden in plain sight, waiting for a theory bold enough to reveal it. Either way, the paradox reminds us that even at the farthest reaches of existence, nothing is ever truly forgotten. The universe keeps its receipts. What if our universe has a cosmic twin, a mirror image where time flows backward and particles are inverted versions of our own? Some physicists believe this might not be science fiction, but a hidden symmetry woven into the fabric of reality itself. The idea hinges on something called CPT symmetry, a fundamental principle suggesting the universe should look identical if you flip three key properties: charge, parity, and time. Reverse a particle's charge, mirror its position, and run the clock backward, and the laws of physics should hold firm. It's like holding reality up to a funhouse mirror and finding the reflection obeys the same rules. But here's where things get wild. If CPT symmetry holds absolutely, it could mean our universe isn't alone. On the other side of the Big Bang, there might exist an anti-universe where time runs in reverse, antimatter dominates, and every star is a shadow of something familiar. Imagine two soap bubbles pressed together at their birth, one expanding forward in time while the other stretches backward. We'd never see this mirror cosmos directly. It's forever hidden behind the singularity of our own beginning, but its influence might linger in ways we're only starting to uncover. One tantalizing clue: dark matter. The invisible stuff that binds galaxies could be the gravitational echo of this anti-universe, its particles interacting with ours only through the gentlest tug of gravity. In this model, dark matter wouldn't be some exotic particle but ordinary matter from the mirror realm, forever out of reach yet shaping the cosmos all the same. It's a radical solution to one of astronomy's biggest puzzles, one that trades mysterious new physics for a cosmic reflection we've yet to glimpse. Critics argue this stretches symmetry too far. After all, we've never observed perfect CPT balance in nature. Our universe favors matter over antimatter, and time's arrow points stubbornly forward. Yet supporters counter that these imbalances might require a mirror universe to restore equilibrium. Think of it like a cosmic ledger. Our excess matter and forward time could be balanced by an anti-universe's antimatter and reversed time, keeping the books of reality in check. The most mind-bending implication: if the anti-universe exists, the Big Bang wasn't a beginning but a midpoint, a moment where two timelines collided and rebounded. In this view, the birth of our cosmos might have been less of a singular explosion and more of a cosmic handshake, with time flowing outward in both directions like ripples from a stone dropped into a pond. Whether this mirror realm is real or just a mathematical curiosity, it forces us to confront a deeper truth. The universe's edges might not be places, but possibilities where symmetry and strangeness dance in ways we're only beginning to imagine. And if we ever find proof of that reflection, it won't just rewrite cosmology, it'll redefine reality itself. At the heart of our galactic neighborhood, where astronomers expected to find a bustling cosmic metropolis, there's a cavern of nothingness so vast it defies logic. The KBC void, named after the scientists Keenan, Barger, and Cowie who identified it, is a spherical expanse stretching nearly 2 billion light-years across, where galaxies are curiously scarce. To put that into perspective, if you were floating at the center of this void, you'd need to travel the distance of 20 Milky Ways lined up end to end before you'd even reach the nearest significant cluster of galaxies. It's not just empty, it's aggressively empty, as if someone carved out a chunk of the universe and left behind a ghostly bubble. What makes this void so unsettling is its location. We're inside it. Our Milky Way sits about halfway between the center and the edge of this cosmic dead zone, like a speck of dust trapped in a snow globe that raises an immediate red flag. According to the cosmological principle, the bedrock assumption that matter should be evenly distributed on large scales, we shouldn't find ourselves in such a lopsided corner of space. It's like walking into a stadium expecting a crowd, only to realize you're alone in the stands. Theories abound to explain this eerie vacancy. Some cosmologists argue it's a statistical fluke, a random low-density bubble in the grand froth of the cosmos. But the numbers don't quite add up. Simulations of the universe's evolution suggest structures this large and empty should be vanishingly rare, yet here we are, living in one. Others propose a more tantalizing idea. The KBC void might be the scar of a collision between our universe and another in the multiverse. Picture two soap bubbles brushing against each other in a bathtub. Where they meet, their surfaces might repel, creating a temporary void in the contact zone. If something similar happened in the primordial cosmos, it could have pushed matter away, leaving behind this staggering emptiness. Supporters of this multiverse theory point to another oddity, the void's shape. Unlike most cosmic vacancies, which are irregular and porous, the KBC void is remarkably spherical, a geometry that hints at a single cataclysmic event carving it out. If true, we might be staring at the first tangible evidence of a parallel universe, a shadow imprint left by something beyond our own reality, but skeptics aren't convinced. They argue that even if the void exists, attributing it to a multiverse is a leap too far. Instead, they suggest exotic physics closer to home, like dark energy behaving differently in this region or primordial quantum fluctuations gone haywire. There's also the chance we're misreading the cosmic map. Dust and gas in our own galaxy could be obscuring distant galaxies, making the void seem emptier than it really is. Regardless of its origins, the KBC void forces us to confront how little we know about the universe's architecture. If voids this size can exist, what other colossal structures might lurk in the shadows? And if we're truly living in one, does that mean we're the outliers, an accident of cosmic geography? Or is the universe far stranger, far less uniform than we ever dared to guess? The answer might rewrite not just our place in space, but the very rules that govern it. Out in the vast cosmic ocean, galaxies aren't just drifting apart. They're fleeing from each other faster with every passing second, as if space itself is stretching under some invisible, relentless force. This acceleration wasn't just unexpected when astronomers discovered it in the late 1990s. It was shocking. Gravity, after all, should be pulling the universe back together, slowing its expansion. Instead, something we now call dark energy is doing the opposite, pushing galaxies apart at a rate that grows more furious the farther they get. But here's the thing, we have no idea what dark energy actually is. It makes up 68% of the universe's total energy budget, dwarfing everything we can see or touch, and yet it leaves no fingerprints, no light, no particles, no detectable signature. Just an effect so subtle it took the most precise telescopes in history to spot it. So what's driving this runaway expansion? The leading candidate is Einstein's cosmological constant, a sort of energy woven into the very fabric of empty space. Think of the vacuum as a bubbling quantum foam where particles flicker in and out of existence. These fleeting fluctuations could generate a repulsive force, gently nudging space apart. It's an elegant idea, but there's a catch. When physicists calculate how much energy this quantum foam should produce, the number is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in all of science. Either we're missing something fundamental, or dark energy isn't a constant at all. That's where quintessence comes in, a mysterious, dynamic field that might ebb and flow over cosmic time. Unlike the steady push of a cosmological constant, quintessence could change strength, even switching from repulsive to attractive as the universe ages. Some models suggest it caused the universe's expansion to slow down in its youth before revving up again, like a car coasting downhill only to suddenly hit the gas. If true, this would mean dark energy isn't just some static backdrop. It's an active player evolving alongside the cosmos. The problem, we've yet to find any direct evidence for it. Then there's the most unnerving possibility of all, vacuum decay. Imagine our universe isn't in its most stable state, but teetering on a precarious ledge. Quantum fields permeate everything, and if one were to suddenly collapse into a lower energy state, it could trigger a catastrophe. A bubble of true vacuum would expand at the speed of light, rewriting the laws of physics as it goes. One moment stars shine, galaxies spin, the next reality itself unravels. It sounds like science fiction, but the math checks out. The universe's acceleration could be a clue that we're sitting on a quantum time bomb with dark energy as the fuse. The terrifying beauty of this mystery is that it's not just academic. If dark energy strengthens, it could eventually tear apart galaxies, then stars, then atoms in a big rip. If it weakens, gravity might regain control, collapsing the cosmos in a big crunch. Or maybe it'll just fade into obscurity, leaving a cold, empty universe where galaxies blink out of sight one by one. Right now, we're like sailors trying to predict a storm by studying ripples on the water where something huge is coming, but blind to its true shape. Every new telescope, every deeper map of the cosmos brings us closer to answers. But dark energy remains the universe's greatest poker player, holding its cards close, leaving us to guess at the fate of everything. We know the universe is teeming with dark matter and dark energy, but here's something equally baffling: half the normal matter, the stuff that makes up stars, planets, and even us, is missing. You'd think something as fundamental as protons and neutrons would be easy to track. Yet when astronomers tally up all the visible matter in galaxies and clusters, they hit a staggering shortfall. Based on the afterglow of the Big Bang, there should be about twice as much ordinary matter, or baryons, as we've found so far. It's like doing inventory on a warehouse and realizing half the goods have vanished without a trace. So where did it all go? One leading theory points to the cosmic web, the sprawling network of filaments that connects galaxies like threads in a spider's silk. These vast, wispy tendrils are thought to be threaded with superheated plasma, gas so thin and diffuse it's nearly invisible to our telescopes. Picture steam rising from a boiling pot. Individually, each wisp is hard to see, but together they fill the room. In the same way, these baryons might be hiding in plain sight, woven into the universe's scaffolding at temperatures of millions of degrees. Recent X-ray telescopes have even glimpsed faint glows from these filaments, like catching the barest shimmer of heat haze on a desert horizon. But there's another twist. Some of this missing matter could be floating in the voids between galaxies as ultra-diffuse clouds, so spread out they don't emit or absorb enough light to detect. It's like searching for a single snowflake in a blizzard, possible in theory, but nearly impossible in practice. Others speculate that baryons might have been ejected from galaxies by supernova explosions or black hole jets, flung into intergalactic space like confetti in a hurricane. The trouble is, even these violent events shouldn't account for all the missing mass. Then there's the wild card. Could some baryons have transformed into something else entirely? Quantum physics allows for exotic states of matter under extreme conditions, perhaps in the crushing depths of space. Ordinary particles decay into forms we don't yet recognize. Or maybe the missing matter is tied up in primordial black holes, relics from the universe's first second, hiding their weight behind event horizons. The hunt for these vanishing baryons isn't just academic. Finding them would confirm our models of cosmic evolution, proving we understand how matter clumped together after the Big Bang. But if they remain elusive, it could mean we're missing a fundamental chapter in the story of the universe, one where ordinary matter plays a far stranger role than we ever imagined. Every unexplored shadow between galaxies whispers the same tantalizing question: how well do we really know the stuff we're made of? deep within the faint glow of the cosmic microwave background, there's a pattern so peculiar it makes even seasoned cosmologists pause. Tiny, ghostly shadows stretch across the sky, subtle temperature variations that seem to align with something beyond our universe. These streaks, sometimes called dark flow imprints, ripple through the CMB like echoes from an unseen realm, sparking a tantalizing question. Could we be seeing the gravitational fingerprints of other universes brushing against our own? The idea hinges on a phenomenon called the kinematic Sunyaev-Zeldovich effect. When galaxy clusters move en masse through space, they leave faint trails in the CMB distortions caused by scattering cosmic photons. But some clusters appear to be drifting together toward a single patch of sky at velocities that defy explanation, as if tugged by an invisible hand. The strangest part, the direction of this motion doesn't match any known concentration of mass in our universe. It's like watching leaves blown by a wind with no source, hinting at something vast and incomprehensible beyond the cosmic horizon. Supporters of the multiverse theory see this as a smoking gun. If our universe is just one bubble in an endless froth of others, neighboring bubbles might exert gravitational pulls through the fabric of spacetime itself. These phantom tugs could nudge entire galaxy clusters, imprinting their presence on the CMB like shadows cast by unseen giants. Some models even suggest these imprints should form specific patterns, circular cold spots or elongated streaks, like bruises from cosmic collisions in the universe's infancy. Yet skepticism runs deep. Critics argue these anomalies could be statistical flukes, the kind of random noise you'd expect when analyzing something as complex as the CMB. Others point to unaccounted for systematic errors in measurements, like dust in our own galaxy mimicking exotic signals. The Planck satellite, which mapped the CMB in unprecedented detail, found no conclusive evidence for dark flow, leaving the debate unresolved. It's a classic cosmic detective story. The clues are intriguing, but the case remains open. What makes this mystery so electrifying is its sheer audacity. If these shadows do trace back to other universes, it would be the first tangible evidence that reality is far grander than we ever imagined. But if they're mere illusions, they remind us how easily our instruments and our biases can shape the story we tell about the cosmos. Either way, the CMB's whispers keep us listening, waiting for the next clue in a puzzle that might redefine existence itself. The laws of physics tell us the universe should look the same in every direction, no up, no down, no special axis. But what if we're wrong? A handful of studies have unearthed something startling. Faint hints that the cosmos itself might be spinning, rotating like a colossal top across billions of light years. If true, it would shatter one of cosmology's most sacred principles, the idea that the universe is isotropic, perfectly uniform no matter where or how you look. These whispers of rotation first emerged from patterns in the cosmic microwave background. Certain temperature fluctuations appeared ever so slightly skewed, as if stretched along an invisible axis. Later, surveys of distant quasars, bright galactic cores powered by voracious black holes, revealed their light might be polarized along a preferred direction, like compass needles all pointing the same way. The odds of this happening by chance, less than 1 in 1,000. It's as if the universe has a subtle lean, a cosmic tilt we're only just beginning to notice. The implications are staggering. A rotating universe would imply a violation of what's called CPT symmetry, the rule that physics should stay unchanged if you flip charge, parity, and time simultaneously. In simple terms, it would mean the cosmos has a built-in handedness, a fundamental preference for spinning clockwise or counterclockwise. Some theorists call this the axis of creation, a relic imprint from the Big Bang itself. Picture the infant universe not as a uniform fireball, but as a whirlpool, its initial spin frozen into the fabric of space-time as it expanded. But here's where things get truly wild. If the universe rotates, it could challenge our very definition of infinity. a spinning cosmos might curve back on itself like a four-dimensional Klein bottle, finite yet without boundaries. Travel far enough in one direction, and you'd eventually return to your starting point, not by looping through space, but because space itself twists like a Möbius strip. This could reshape our understanding of dark energy, galaxy formation, even the arrow of time. Critics, however, aren't convinced. They argue these anomalies could stem from measurement biases or unaccounted for distortions in interstellar dust. After all, finding a preferred direction in the universe is like declaring north is special on Earth. It's only meaningful relative to our perspective. Others suggest the signals might trace back to quantum fluctuations in the early universe, stretched to cosmic scales by inflation. Yet the possibility lingers, haunting the edges of our maps. If the universe does spin, it would mean we're not just floating in space, we're caught in a slow, grand pirouette, dancing to a rhythm set 13 billion years ago. And somewhere out there, beyond the veil of the observable, that primordial rotation might still be winding down, a whisper of the moment when reality first began to turn. If the universe is teeming with life, as many scientists believe, then where is everyone? This is the Fermi paradox in a nutshell, the puzzling contradiction between the high probability of extraterrestrial civilizations and the total lack of evidence for them. But what if the answer lies not in the cosmic centers where stars cluster thickly, but out at the very edges of existence? If intelligent life arises often, why wouldn't species living near the universe's fringes have reached out by now? The unsettling truth might be that the edge isn't just empty, it could be a dead zone, a place so inhospitable that even advanced civilizations wouldn't survive long enough to make contact. Consider the challenges of living on the frontier. As the universe expands, galaxies at the very edge are hurled away from us faster than light can bridge the gap. Any civilization born there would watch the rest of the cosmos vanish over an unreachable horizon, leaving them trapped in an island of shrinking resources. Stars would age and die, new ones wouldn't form, and the night sky would grow darker with each passing eon. It's a slow-motion apocalypse where entropy wins not with a bang but with a whisper. Even if a society developed the means to travel between stars, they'd face an inescapable truth. The universe's expansion is a one-way trip into isolation. But there's another, even stranger possibility. What if the edge isn't just harsh? What if it's quarantined? Some theorists speculate that advanced civilizations might deliberately avoid regions where space stretches toward oblivion, treating them like cosmic dead ends. Think of it like ancient sailors steering clear of the edge of the map, fearing the unknown. Or worse, imagine that something already lurks in those distant voids, a force or intelligence that keeps the frontier silent. Could the great filters preventing life from thriving, like self-destruction or resource collapse, be even more ruthless at the universe's fringes? Then there's the eerie scenario where edge-dwelling civilizations have tried to reach us, but their signals are lost to the unstoppable expansion of space. Light from the outer reaches might be stretched into undetectable wavelengths, or their messages could take billions of years to arrive, only to pass through our region of space when no one's listening. We might be like two ships adrift in a hurricane, radios blaring but separated by a storm that drowns out every call, the most unsettling answer of all. We could be alone not because life is rare, but because the universe itself is designed to isolate. If the edge is where physics frays, where dimensions twist, or where time itself behaves unpredictably, then the cosmos might be subtly engineered to keep civilizations apart. Whether by natural forces or something more deliberate, the vast stretches between galaxies could be less an accident of space and more a cage. The Fermi paradox's edge twist forces us to confront a chilling thought. We might not hear from alien civilizations because the universe won't let us. And if that's true, the silence isn't just an answer, it's a warning. We think of the Big Bang as the ultimate beginning, the moment when time, space, and matter exploded into existence. But what if it wasn't the start at all? What if our universe is just one chapter in an endless cosmic cycle, or worst, a random bubble that popped out of absolute nothingness? The truth is, science has no answer for what came before the Big Bang. Time as we know it may have started then, but that doesn't mean reality did. Some theories suggest our universe has been bouncing like a cosmic yo-yo for eternity. In these cyclic models, each Big Bang is just the rebound from a previous collapse, a universe crunching down to an ultra-dense speck before exploding outward again. Imagine a pendulum swinging back and forth forever, where every swing is a new cosmos being born from the ashes of the last. But there's a twist. Modern physics hints that these cycles might not be perfect copies. Dark energy's relentless push could mean each new universe stretches farther and emptier than the one before, like a balloon losing air with every reinflation. If true, our universe might be one in a dwindling lineage, destined to leave no offspring in the cosmic family tree. Then there's the quantum foam hypothesis, where reality isn't a series of bangs but a seething ocean of virtual universes. At the tiniest scales, empty space isn't empty, it's a chaos of particles flickering in and out of existence. Some theorists propose that our universe could be one of those quantum fluctuations, blown up to cosmic proportions by a random surge of energy. Picture a bubble forming in boiling water, but instead of popping, it keeps expanding indefinitely. The most mind-bending idea that the Big Bang emerged from pure nothingness, no time, no space, no rules. Philosophers call this creatio ex nihilo, creation from nothing, and it's as baffling as it sounds. Quantum mechanics allows for particles to appear spontaneously if they vanish quickly enough. So could the universe itself be the ultimate quantum accident? The math suggests a universe like ours might indeed have zero net energy, the positive energy of matter and motion, perfectly balanced by the negative pull of gravity. In that case, our entire existence could be a grand cosmic free lunch, borrowed from nothing and owed to no one. Yet these theories all dance around the same unsettling truth: we might never know. The Big Bang's initial conditions erased any traces of what came before, like a fire burning away its own origins. Even if other universes exist beyond our cosmic horizon, their light may never reach us across the infinite stretch of expanding space. The before might be forever locked away, leaving us with only echoes and guesses. For now, the question lingers not just as a scientific puzzle, but as a humbling reminder that some mysteries resist even the brightest human mind. The universe may have answers, but it isn't in a hurry to share them. One day, in the inconceivably distant future, the last star in the universe will flicker out. The skies will go dark, temperatures will plummet toward absolute zero, and the cosmos will enter its twilight, a state scientists call heat death. But is this frozen oblivion truly our universe's inevitable fate? Or are there other, far more violent endings lurking in the equations of physics? The answer depends on the unseen forces tugging at the fabric of reality itself. First, there's the Big Crunch, a dramatic reversal of cosmic expansion where gravity finally wins the ultimate tug of war. Picture the universe as a rubber band stretched to its limit. If dark energy weakens and matter's pull gains the upper hand, that rubber band could snap back, collapsing galaxies, stars, and even space-time into a singularity hotter and denser than the Big Bang itself. This scenario isn't just an ending, it could be a reset button, recycling the universe's remains into a new explosion. A cyclical cosmos where every death births another beginning. But here's the catch. Current observations suggest dark energy isn't weakening, its accelerating expansion, making the crunch seem less likely with each passing eon. Then there's the Big Rip, a far more unsettling finale. If dark energy grows stronger over time, it won't just push galaxies apart, it will shred them. First, galaxy clusters would be torn asunder, then individual stars, then planets. In the final microseconds, atoms themselves would disintegrate as the repulsive force overwhelms the glue holding nuclei together. The universe wouldn't just end cold and empty. It would explode in a cascade of annihilation, leaving behind a scattered sea of lonely particles too far apart to ever interact again. But the most unsettling theory isn't a slow freeze or a violent rip, it's a cosmic time bomb hidden in the vacuum of space itself. Quantum fields permeate the universe, and if one of them isn't perfectly stable, a bubble of true vacuum could form anywhere, anytime. This bubble would expand at light speed, rewriting the laws of physics in its wake. One moment you're sipping coffee, the next reality as you know it ceases to exist, not with a bang but with a silent, inescapable rewrite. Yet amid these apocalyptic visions, a glimmer of hope persists. Some models of string theory suggest our universe might be one page in an infinite multiverse book, where death in one realm means birth in another. Others propose that quantum fluctuations in the far future could spark new Big Bangs, birthing fresh universes in the graveyard of our own. The terrifying beauty of these theories is that they force us to confront a paradox. Even as we map the universe's demise, we're left wondering if endings are ever truly final, or just doorways to realities beyond our comprehension. What if every star, planet, and atom in the universe is nothing more than a hologram, a shimmering projection from some distant cosmic boundary? This isn't science fiction. It's a legitimate theory born from the marriage of black hole physics and string theory, and it suggests reality as we know it might be a grand illusion. The holographic principle dares to propose that everything unfolding in our three-dimensional world, every supernova, every galaxy collision, even your thoughts right now, could be encoded on a two-dimensional surface at the edge of existence. But if that's true, where exactly is this cosmic projector screen, and who or what is running the simulation? The idea emerges from an astonishing discovery about black holes. When matter falls into one, it doesn't just vanish. It leaves behind an imprint on the event horizon, the point of no return. Like a fingerprint pressed into wet clay, every particle's information gets smeared across this boundary in vanishingly tiny bits. Physicists realized this could mean the horizon isn't just a barrier, it's a hard drive, storing data about everything inside. Take this logic to its extreme, and the entire universe might work the same way. A three-dimensional movie projected from instructions written on some faraway two-dimensional surface. String theory takes this even further. In its framework, the universe could be like a vibrating guitar string, with different notes corresponding to different particles. But these strings might live on the edge of a higher dimensional space we can't perceive, like shadows cast on a cave wall. Imagine scribbling a message on a piece of paper, then crumpling it into a ball. The words are still there, just scrambled into a new form. Similarly, the cosmos we experience could be a crumpled-up version of information stored neatly at the boundary. The most mind-bending part, this isn't just poetic speculation. Math backs it up. Equations describing events inside a volume of space can be perfectly mirrored by equations describing fluctuations on its surface, a duality so precise it's convinced many physicists there's fire beneath this smoke. If true, the universe's edge wouldn't just be a place, it would be the ultimate archive, a cosmic library of Alexandria holding the blueprints for every quark, every supernova, every breath ever taken. But here's where the mystery deepens. If reality is a projection, what's the nature of the screen? Some theorists argue it's the boundary of our observable universe, a sphere centered on Earth with a radius of about 46 billion light-years. Others propose it's the surface of a higher dimensional bubble in the multiverse, where our universe is just one holographic sticker in an infinite scrapbook. Then there's the startling possibility that the screen isn't fixed at all. It's dynamic, stretching and warping as the universe expands, rewriting itself in real time like some celestial etch-a-sketch. The implications are staggering. If the holographic principle holds, it would mean the universe has a built-in resolution limit, a pixel size so fine we've yet to detect it. Just as a digital image blurs when you zoom in too far, space-time itself might dissolve into grainy uncertainty at the tiniest scales. Some experiments, like those hunting for quantum jitters in space-time, could soon test this. And if they find evidence of pixels in reality's fabric, it would be the first clue that we're not just in the universe, we're of its boundary, living in a shadow play cast by forces beyond our sight. Yet for all its elegance, the theory leaves us with a haunting question: what lies beyond the screen? If we're projections, what's projecting us? Is it some vast cosmic computer, as simulation theories suggest? Or is the boundary itself a kind of mind, a self-organizing system encoding its own existence? The holographic principle doesn't answer these questions, but it redefines them, turning the edge of the universe from a mere horizon into the most important place in existence. After all, if the boundary holds the code for everything within it, then in a very real sense, the center of reality isn't inside the cosmos, it's outside, written in symbols we're only beginning to decipher. Among the countless particles swirling through the cosmos, there's one that should exist but stubbornly refuses to show itself: the magnetic monopole. Unlike ordinary magnets, which always come with inseparable north and south poles, these elusive entities would carry just a single magnetic charge, a fundamental magnetic electron, if you will. Theory insists they should be everywhere. The grand unified theories that stitch together the forces of nature predict they'd have formed in droves during the universe's fiery infancy, littering space with relics as common as atoms. Yet after decades of searching, from deep underground labs to cosmic ray detectors, not a single confirmed monopole has turned up. Their absence isn't just a curiosity, it's a gaping hole in our understanding of physics, forcing us to ask, did something erase them, or did we get the universe's blueprint all wrong? The case for monopoles begins with the early cosmos, a seething cauldron of energy where temperatures soared beyond 1 trillion degrees. In these extreme conditions, physicists believe the four fundamental forces, electromagnetism, gravity, and the strong and weak nuclear forces, were fused into a single, unified interaction. As the universe expanded and cooled, these forces froze out one by one, like layers of ice forming on a lake. Each phase transition should have left behind defects in spacetime's fabric, cosmic cracks where symmetry broke imperfectly. Monopoles are one such defect, topological knots in the quantum fields that refuse to untangle. Estimates suggest the young universe would have forged them so prolifically that today, they'd outnumber protons by a factor of 10 billion. Your body alone should contain hundreds. The fact that we haven't found even one is like searching an ocean and finding no fish, only drier sand. This glaring mismatch led physicists to one of the most radical ideas in cosmology: inflation. To explain the monopole shortage, they proposed that the infant universe underwent a fleeting but exponential growth spurt, ballooning from subatomic size to macroscopic scale in a fraction of a second. This explosive expansion would have diluted monopoles to near non-existence, scattering them so thinly across space that finding one becomes a needle in a haystack challenge. Inflation neatly solves the monopole problem, but at a cost. It requires ad hoc assumptions about unknown energy fields and leaves behind no direct evidence of its own. Worse, some versions of the theory predict we should still detect a few monopoles, just at lower densities. Yet our detectors remain silent, their sensors aching with emptiness. That silence has sparked alternative explanations. Maybe monopoles decayed over time, their magnetic charge leaking away into extra dimensions we can't perceive. Or perhaps they clumped together in the early universe, forming massive structures that later collapsed into monopole black holes, hiding their traces behind event horizons. Some theorists even speculate that monopoles aren't missing at all. They're just invisible to our current tools, their signatures masquerading as dark matter or other anomalies. The wildest idea that our understanding of grand unified theories is fundamentally flawed, and the forces never merged in the way we thought. If true, it would mean rewriting textbooks on particle physics from the ground up. What makes this mystery so electrifying is what it reveals about science itself. The hunt for monopoles isn't just about ticking a box on a theoretical checklist. It's a stress test for our boldest ideas about the universe's origins. Every null result, every empty detector forces us to rethink the assumptions we've taken for granted. Whether monopoles are hiding in plain sight or never existed at all, their absence is a ghostly fingerprint pressing us toward deeper truths. And if we ever do find one, it would be a discovery on par with the electron or the Higgs boson, a key to unlocking forces that shaped reality itself. Until then, the universe keeps its magnetic secrets close, leaving us to wonder if the missing pieces are lost, or if we've been searching the wrong puzzle all along. Zoom in far enough, past atoms, past quarks, past anything we've ever detected, and reality itself might dissolve into chaos. At scales a trillion times smaller than an atom, space-time could be a seething, frothing ocean of turbulence known as quantum foam. This isn't just empty space, it's a frenzy of virtual particles blinking in and out of existence, microscopic wormholes forming and collapsing, and the very fabric of dimensions twisting like a writhing knot. The foam gets its name from the way it resembles the froth on a stormy sea, a churn so violent that the concepts of here and now lose all meaning. If this frenzy extends to the universe's edge, it raises a jaw-dropping possibility. The foam might not just be a curiosity of the ultra-tiny, it could be the ultimate cosmic barrier, a wall of pure chaos where existence itself frays into noise. The idea traces back to quantum mechanics and general relativity's most brutal turf war. Down at the Planck scale, distances of 10 to the power of -35 meters gravity and quantum forces battle for dominance, creating fluctuations so intense they warp the bedrock of reality. Imagine stretching a rubber sheet taut, then blasting it with microscopic firecrackers. That's space-time at this level. These aren't mere mathematical quirks. If quantum foam is real, it could mean the universe's edge isn't a clean boundary, but a fractal mess of probabilistic frenzies where the very idea of beyond becomes nonsensical. There's no smooth frontier, just an infinite regress of turbulence, like trying to find the edge of a cloud by walking into it. This raises a haunting question. Is the foam nature's way of preventing anything from existing past a certain point? Some models suggest that at the Planck scale, spacetime's fluctuations grow so wild that distances and durations can't stabilize. It's not that there's nothing on the other side of the edge, it's that other side ceases to be a coherent concept. Time might shatter into fragments with cause and effect twisting into loops. Space could become a hall of mirrors where every direction folds back on itself. In such a realm, the very ingredients needed for existence-stable dimensions, predictable physics, would dissolve like sugar in boiling water, yet there's an even wilder twist. If quantum foam dominates the edge, it might not be a barrier at all but a gateway. Some interpretations of string theory suggest these turbulent zones could birth baby universes, budding off from our own like bubbles in a glass of champagne. Wormholes, those legendary shortcuts through spacetime, might flicker into being here, stitching together distant regions of reality, or even different realities entirely. The foam's chaos could be creative, a cosmic forge where new physics are hammered into shape, but proving any of this is a nightmare. Planck-scale physics operates so far beyond our instruments that detecting quantum foam directly is like trying to hear a whisper in a hurricane. Even indirect evidence is sparse. Some experiments hunt for traces of spacetime's graininess in high-energy cosmic rays or quantum-entangled particles, but so far the foam remains elusive. It's a ghost in the equations, a specter haunting the edge of our understanding. What makes this mystery so tantalizing is its sheer defiance. The quantum foam doesn't just challenge our models, it obliterates the language we use to describe reality. If the universe's edge is a storm of probabilistic mayhem, then the very questions we ask about what lies beyond might be flawed. We're like flatlanders trying to imagine the third dimension, groping for concepts that don't exist in our framework. Until we crack the foam's code, the edge remains the ultimate cosmic mirage, always receding, always shifting, forever just out of reach. Deep in the patterns of galaxy clusters, buried in the cosmic web's grand design, there's an echo from the universe's infancy, a whisper of sound frozen in time. These are Boörean acoustic oscillations, ripples left over from a period when the cosmos was so dense and hot that matter and light were locked in a deafening dance. Picture the early universe as a seething plasma, photons shoving against protons in a pressure wave that raced outward at half the speed of light. When the universe cooled enough for atoms to form, releasing light as the cosmic microwave background, these waves froze mid-reverberation, leaving behind ghostly shells of clustered matter. Today, those ancient echoes linger as a subtle preference in galaxies, spacing a tendency for galaxies to gather about 500 million light-years apart, like beads strung along invisible wires. This pattern isn't just a fossil, it's a cosmic yardstick. By measuring these oscillations, astronomers can gauge distances across the universe with astonishing precision, much like using the regular ticks of a metronome to map the size of a concert hall. But here's where it gets eerie. The scale of these oscillations could hold clues to something far grander: the universe's ultimate size and shape. If space is finite and curves back on itself, like the surface of a four-dimensional balloon, these sound waves might eventually wrap around, overlapping in ways that reveal the cosmos's true scale. Imagine shouting in a closed room and hearing your voice echo back at a predictable interval. The universe's sound waves could, in theory, do the same. Yet the data refuses to cooperate. When scientists map these oscillations across billions of light-years, they find no sign of repetition, no telltale folds hinting at a finite cosmos. Instead, the patterns stretch on, unbroken, as if space truly is infinite. But there's a catch: our observable universe might simply be too small to detect the curve. It's like standing in the middle of an endless desert and trying to deduce the Earth's roundness from the flat horizon. You'd need to see much farther to spot the bend. Future telescopes, like the upcoming Square Kilometre Array, could extend our vision, hunting for subtle warps in these acoustic ripples that might betray the universe's hidden geometry. Even stranger, these oscillations might encode secrets about what lies beyond our cosmic horizon. Some models suggest that if another universe brushed against ours in the distant past, the collision could have left scars in the Boörean waves' distortions that skew the spacing of galaxies in specific directions. It's a long shot, but if proven, it would mean the universe's sound isn't just an echo of the past, it's a message from realms we can't yet see. What makes these oscillations so extraordinary is their duality. They're both a relic and a tool, a whisper from the Big Bang and a measuring tape for the cosmos. Every galaxy survey, every 3D map of the universe's large-scale structure adds another layer to their story. And as we listen closer, we might just discover that the universe isn't silent, it's singing, and its song holds the keys to mysteries we've only begun to imagine. Picture the universe's edge not as a sharp boundary, but as a vast, silent ocean, one made not of water, but of dark matter. This invisible substance, which outweighs normal matter 5-to-1, might not be spread evenly across the cosmos. Instead, some theories suggest it could accumulate at the farthest reaches of space, pooling like cosmic dew on the edges of reality. If true, this dark matter ocean would warp the very fabric of existence in ways we're only beginning to imagine. Galaxies forming near this shadowy frontier would face a gravitational landscape unlike anything we see closer to home. Normally, dark matter acts as an invisible scaffold, its gravity helping gas and dust clump together into stars and galaxies. But at the edge, where dark matter could be denser and more sluggish, that process might go haywire. Picture a whirlpool forming in molasses instead of water. The drag would slow everything down. Stars might birth more slowly, galaxies could grow lopsided as gravity pulls unevenly, and entire clusters might drift like ships caught in an invisible tide. Some models even suggest these borderland galaxies could appear stretched or warped, their light bent by the dense dark matter they're swimming through. And then there's light's journey. Photons traveling from the universe's edge toward Earth would have to pass through this murky dark matter sea. Normally, dark matter doesn't interact with light, but if even a tiny fraction of it possesses some unknown property, perhaps a feeble connection to photons, the effects could be profound. Light might lose energy as it fights through the dense medium, redshifting farther than expected, or it could scatter in odd directions, making distant galaxies appear fainter or more distorted than they really are. Astronomers mapping the cosmic microwave background have already spotted anomalies in the polarization patterns near certain voids. Could these be ripples from light skimming the surface of dark matter oceans at the edge? The wildest possibility, this dark matter ocean might not be static. Some simulations suggest it could slosh and churn, creating waves or currents that push galaxies around over billions of years. Entire galactic superclusters might be adrift in these unseen tides, their motions hinting at forces we can't directly detect. There's even a chance that collisions between universes, if such things occur, could send shockwaves through this dark medium, leaving scars in the distribution of galaxies we're only now learning to read. Yet for all its mystery, this ocean might hold clues to dark matter's true nature. If we could study how it pools and flows at the edge, we might finally glimpse its particles' properties, whether they're cold and slow-moving, warm and energetic, or something even stranger. The universe's boundary isn't just where light fades. It could be where dark matter finally steps into the spotlight, revealing secrets it's kept hidden since the dawn of time. Here's a chilling thought. What if you're not actually watching this video, but are instead a fleeting hallucination, a random fluctuation in the void? That's the essence of the Boltzmann brain paradox, a cosmic riddle so unsettling it makes philosophers tremble. Named after the 19th century physicist Ludwig Boltzmann, this idea starts with a simple premise: given enough time, even the most improbable events become inevitable. In an infinite or near-eternal universe, particles bouncing around at random could theoretically arrange themselves into a fully formed, self-aware brain complete with false memories of a past that never existed. Not just once, but an infinite number of times. By sheer chance, you could be one of those momentary aberrations, convinced you're real when in fact you're just a statistical blip in the darkness. But why does this matter for the edge of the universe? Because the paradox forces us to confront a brutal question. If reality is infinite, why don't we see more randomness on display? Why is the cosmos so orderly, so structured, when chaos should dominate? One possibility is that we're not in an infinite universe at all. We're near the edge, in a region still young enough for coherence to hold. Think of it like standing near the shore of a vast ocean. The water closest to land is calm, but farther out, the waves grow wild and unpredictable. If we were truly adrift in an endless sea of space-time, the odds of being a Boltzmann brain would dwarf the odds of being a real, evolved consciousness. The fact that we're not drowning in hallucinations might hint that infinity is an illusion, that somewhere out there, the universe has boundaries keeping the chaos at bay. Then there's the nuclear option. Maybe our entire framework of cosmology is flawed. The paradox assumes the laws of probability hold universally, but what if they don't? Quantum mechanics already tells us observation shapes reality at microscopic scales. Could there be some deeper principle preventing self-aware flukes from arising? Some theorists suggest consciousness itself might act as a filter, a kind of cosmic immune system that suppresses Boltzmann brains before they can form. Others argue the paradox is a reductio ad absurdum proof that infinite universes or eternal inflation can't be real because they lead to conclusions that defy lived experience. The terrifying beauty of this puzzle is that it straddles the line between physics and philosophy. It's not just about particles and probabilities, it's about the nature of existence itself. If Boltzmann brains are more likely than real minds, then every scientific observation, every memory, every moment of introspection could be a mirage. The universe's edge might not be a place but a safeguard, a barrier against the absurd. Or perhaps the paradox is simply a mirror reflecting our own limitations. After all, if the cosmos is truly infinite, we're left with a humbling truth. Some mysteries aren't meant to be solved, only pondered in the dark. From the eerie silence at the edge of the observable universe to the phantom pull of dark flow, from cosmic voids where nothing should exist to the holographic code that might underpin reality itself, we've journeyed through 30 mysteries that defy everything we thought we knew. Each one is a crack in the foundation of modern physics, a whisper that the cosmos is far stranger, far grander than our textbooks dare to admit. These aren't just puzzles, they're doorways. The Great Attractor's gravitational enigma, the cold spot's multiverse tease, the quantum foam churning at spacetime's smallest scales, every one of them forces us to rethink the nature of existence. And here's the thrilling part, we're not just passive observers. Every telescope trained on the night sky, every detector buried deep underground, every equation scribbled on a chalkboard brings us closer to unraveling these riddles. Think of it like this: 500 years ago, explorers drew maps with edges labeled, "Here be dragons." Today, our dragons are made of dark matter. Our uncharted territories stretch across billions of light years, and our ships are equations and silicon sensors. The difference: those ancient cartographers were wrong about the monsters. Ours might be real. The universe's edge isn't just a boundary, it's a mirror reflecting back all the things we don't yet understand. And that's the beauty of science. Every answer spawns new questions, every discovery reveals deeper layers. So stay curious, because the next breakthrough might come from a graduate student staring at a data glitch, a retired engineer tinkering in a garage, or you, watching this video and wondering what's out there. The universe hasn't finished surprising us. In fact, the biggest revelations might be hiding in plain sight, waiting for someone to connect the dots. Whether it's a hidden dimension curled up inside an atom, a parallel universe etched into the cosmic microwave background, or a law of physics we've yet to name, one thing's certain: the cosmos is richer, weirder, and more alive with possibility than we've ever dreamed. The edge isn't the end, it's just the beginning.